Okay, our first example says that I find the vertical displacement at point A and point C. So we've been given a structure that is made up of a cantilever beam, and then point A is at the extreme end, and then point C is at this point, is at the middle. So what do? We are going to be following the 3 steps that we said we take in calculation. So if we are to start to answer this question, let's look at the first step. Like we say that what do? We say that we draw the bending moment diagram due to the action of the original load. So assuming that this is our beam, and then this is the force, the force Fp. Then the bending moment diagram for this structure here would be of this nature, as familiar to us. It would be a right angled triangle, and then the value of the moment at this point here would be FPL, like that. So after drawing the bending moment diagram due to the original loading, say for example this is M, now we come and draw the bending moment diagram at the point whose displacement is required. That is, if we are considering point A, we say that you add a unit force. You add a unit force at that point. So if this is point A, we add a unit force there, which is F is equal to Fp is equal to 1. So we come and draw the bending moment diagram due to the action of this unit force. It would be of the same shape as the top one. The magnitude would be what? The magnitude would be Fp, which is 1 times L. So we shall be having L here. So we say that after we do this, what do we do next? We come and find the area. And we say that the area is calculated from the bending moment diagram of the original loading. So for this case, that the bending moment diagram with the original loading is this one under the action of Fp. So the area of the shape would be area is equal to a half BH. So this would be equal to a half by our base, which is F, which is L, then times our height, which is FPL. This gives us 1/2 FPL squared. Yeah. Then we say that the Y is calculated from the bending moment diagram of the action of the unit force. Then to find the Y, we come and determine the position of the center of gravity of the shape. So for a triangle, we say that it will be at a distance a third L from this very point here where we have the right angle. So that would be somewhere here. This way we have the center of gravity, of this shape here. So we come and draw a line downwards, and then so the Y is the distance. The Y is the distance through the center of gravity from the upper boundary of the structure up to where we have the boundary line of the bending moment diagram. So for this shape, it would be this distance here, like this one here. So if you know that this is a third L, that means this other side would be 2/3 of L. So therefore, if this is Y, we can use similar triangles to come and find the height. So our Y, so if we take our Y like the height, divided by the height of the bending moment, diagram, this would be L. Then this would be equal to, now we come and divide by the bases. If I consider this small triangle here, which has got the Y, this would be divided by 2/3 L. Then divide by the length of the entire bending moment diagram, that would be L. So therefore here we come and derive it that Y is equal to 2/3 L. Thus the displacement at point A, delta, would be equal to 1/EI summation of A times Y. This would be equal to 1 over EI into a half FPL squared times 2 over 3 L. So the 2 and 2 would cancel, giving us the overall displacement delta A as 1 over EI into FPL cubed divided by a 3. This also can be written as 1 over 3 EI FPL cubed. Then next we come and look at the displacement at point C. So we come to point C. So we take on the same procedures. What we said, we said that we first have to draw the bending moment diagrams. Say we are beginning with still that of the action of the original load, that was of the value Fp. Here we shall be having a magnitude of FPL for the moment. Then now, like for the sake of the action, then like the next one, they wanted us to find the displacement at point C. So what do? We add a unit force, Fp is equal to 1 at the point whose displacement is required. Then we come and draw its bending moment diagram. So its bending moment diagram would be of this nature, but now the magnitude of moment would be a half of L. So after doing that, we go on with the next steps, finding the area. Okay, so after drawing the bending moment diagrams, you come and try to look at the two shapes. When you look at the shape of this first one here, like this line spans from this point up to this one, isn't it? Up to the very end here. But for the sake of this one, it is only a straight line from here up to here, and then from here up to here, meaning that over the span of this beam here, this bending moment diagram for the unit force is not continuous. It has got a bend or a turning point at this place here. So that means that we've got to divide the bending moment diagram on top here. So we should always take note of that in case there is discontinuity in the shapes, we've got to divide the bending moment diagram. So we come and divide it from this point, like the center point, which is here like this. So after dividing it, this one here becomes a basic shape, so I name it 1. But now when I look at this side here, I form a trapezium. A trapezium is the basic shape. We say that the best way to make it become a basic shape, we come and convert it into a rectangle, and into a triangle. So assuming that this one here becomes 2, and then this one here is taken as 3. Then now when we come to this lower shape here, we only have a right angle triangle, which is already a basic shape. So yeah, then for the sake of this part here, like the y of automatically would be equal to a 0 since we have no height. So next, what do? We come and find the areas from the original loading bending moment diagram. Area A1 for the triangle would be given by a half BH here. So from using the similar triangle approach, we find it that the height of this triangle here would be a half FPL, as in like they take on the same ratios. So meaning that here our area would be equal to a half, then times our base, which is L over 2, then times FPL. So this one here would be giving us the area as FPL over 2. It would be giving us the area as 1 over 8 FPL squared. But then the y, if you come and draw a line from the center coming downwards to come and determine the y, like you discover that the y is a 0. So y1 is equal to a 0. Then we come to the second shape. A2 would be equal to base times height. that would be L over 2, then times the height, which would be a half F P L. So this one here would be giving us a value of 1 over 4 F P L squared, FPL squared. Then our y2 would be equal to, so we come to the triangle, it has got its center right at this point, so this would be right at this point. So if I draw a line downwards here like this, my y2 is expected to be somewhere here like this. So this is y2. So we know that from here up to here would be L over 4, if this is L over 2. So when I use the approach of similar triangles, this would be L over 4. Okay, so using the approach of similar triangles, I would be having y2 divide by this would be L over 4 is supposed to be equal to a half L, then divide by the length. Sorry, if a triangle is called the height, divide by the height of this entire triangle is also L over 2. L over 2. So this gives me y2 is equal to L over 4. So that means our y2 here would be 1 over 4 of L. Then we come now to our third shape. So our area A3 would be given by a half times our base, which is equal to a half F P L, then times our height, which is L over 2. So this gives us 1 over 8 F P L squared. Then our y3 would be equal to, we still take on the same approach and then use similar triangles to come and find the y3 that is for this triangle here. So you come and draw it downwards here. So our y3 would be somewhere here like this. So from this point up to this point, we shall be having it's supposed to be 1 over 3 L, but then our L is equal to L over 2. So as in like it's a 1 over 6. 1 over 6 from this point up to this point. So we come and use similar triangles. We shall be having y3 divided by the height of the bending moment diagram. That would be a half L. This is supposed to be equal to, so the base of the triangle whose height is y3 would be L over 3. That is got from a half minus 1 over 6. So divide by the base of the whole bending moment diagram of the action of the unit force, which would be a half L. So therefore y3 would be given by L over 3. So here we shall be having L over 3. Therefore, my displacement at point C would be given by 1 over EI into we shall be having A1 Y1 plus A2 Y2 then plus A3 Y3. From observation, we can see that the two bending moment diagrams are exactly on the same side of tension, so all the signs would be positives. So this would be equal to 1 over EI into A1 that would be 1 over 8 FPL times 0, that would be a 0. So let's just write from A2. So that would be 1 over 4 FPL squared, then times 1 over 4 L, then plus this should be 1 over 8 FPL squared times L over 3. What do we get? We get it that delta C would be equal to 5 over 48 FP L cubed over EI. Writing it in the beta form, it would be 5 over 48 EI times FPL cubed. So basically that is how we would deal with such a number.